Alright, this is video 2 for the Nuclei and Radiation Radioactivity unit. So in this one, we need to talk about how radiation can damage the body. So we're going to use a unit called the REM. Now, the biological damage done to cells by, cells hit by radiation is measured with this unit called REM. So if we take a look at this infographic here, we have a lot of different types of units that we could use. There's the rad, the gray, all of these. So basically, what it comes down to is we've got absorbed dose right here. So it's like an energy concentration. And then the biological impact, which is the REM. So when we talk about like the energy from radiation, we use units like rads and grays. But when we talk about damage done to people or animals or living tissue, that's where we talk about units like REM and sieverts. So many people estimate that the exposure to one REM to every cell of your body, so we call that a whole body exposure, will increase your chances of getting cancer by 0.04%. That's really not, it's very significant. So if your entire body was exposed to one REM, really it's not so much of exposed, but if your body absorbs, if we go back to the dose equivalent for biological impact there, if your body absorbs one REM of radiation, your chances of getting cancer increase by 0.04%. Another unit that we use for measuring the damage done by radiation is a sievert, and it's a larger unit. 100 REMs equals 1 sievert. I'm going to stick with REMs just to keep everything the same. All right, so let's say you're exposed to something that's below 100 REMs. If you're exposed to something that's below 100 REMs, as far as we know, there's no short-term illness. (100 to 200 REMs), there will be a slight or no short-term illness. You would begin to feel nausea and loss of hair. This is really, the ones that you see in the movies a lot. This is rarely fatal. 300 REM, and you have a 50% chance of death if you go untreated within 60 days. And really what the treatment is a blood transfusion. They replace your blood. If it's more than 1,000, if you're exposed to more than 1,000 REMs, you'll become incapacitated within an hour, 1 to 2 hours, and your survival would be very unlikely. So, as you might imagine, not very many people are exposed to those levels of radiation. So, the real danger is cancer. So the average dose that it takes to induce cancer is a whole body dose of 200 or 2,500 REM. This is a best estimate, and we're not going to be doing tests on people. And this is still an active area of research as well. But it takes 2,000, as far as we know, it takes 2,500 REMs of radiation to automatically give you cancer. But remember, 1,000 REM kills you. So how can anyone get cancer from radiation? That's a very important question. So what we believe the solution to be is that even with a small dose, there is a proportionate chance that cancer will be induced. And we call this the linear effect. So, suppose you are exposed to 25 REMs. If you think about it, you wouldn't even feel this because it's below 100% or below 100 REMs. So if you are exposed to 25 REMs, that is a 1% of a 2,500 REM dose. So what happens then, you will not feel it, but you will now have a 1% additional chance of getting cancer. Now, I say additional, and that's because starting out, everyone has a 20% chance of getting cancer. So everyone starts off with that 20% chance. If you're exposed to 25 REMs, you now have a 21% chance of getting cancer. So looking at this graph right here, the dots indicate the probability of excess cancers from the dose shown. The horizontal axis, or I'm sorry, the horizontal axis gives you the dose. The vertical lines below each point gives you the uncertainty. So that's this right here. So these bars here are the uncertainty. So there's quite a lot of uncertainty in this. The vertical lines, and then the straight line passes through most of the data. So basically, what this graph shows us then is the idea that it's proportional. You know, the idea that getting cancer becomes proportional. So we call this the linear effect. Now, if we take a look at 100, at the 100 REM, for 100 REM, that's a 4%. You know, it's 4% of 2,500. So it gives us a 4% chance of getting cancer. 25 REMs is a 1% chance. Now that's according to the data or the line on this graph. But again, there's a lot of uncertainty in here. You know, it's not always true. So what the linear hypothesis then tells us is that the linear effect is valid, you know, or is that linear effect valid for extremely low doses? If you are exposed to 2.5 REMs of radiation, will you get a 0.1% chance increase to getting cancer? We know that high doses of radiation are bad. We do know that. But what about the really low doses? So maybe like the doses you're exposed to during a dental x-ray, or while you're flying, or working in a hospital's cancer treatment center. Is this linear hypothesis true? So again, you know, if you're exposed to 2.5 REMs, how does that change your effect of getting cancer? Well, 2.5% is 0.1% of a cancer dose, 2,500. So now you're up to 20.1%. Was it that 2.5 REM exposure? Was that the cause of getting cancer? It's hard to tell at these really low doses. And again, it comes from uncertainty. We don't know if the linear hypothesis holds true for low doses of radiation, but it's better to be safe than sorry. So in the U.S., we design our radiation policies, the things that the government comes up to help keep us safe. We design our um, things around the linear hypothesis, and we assume it to be true. And that's how we design nuclear policy for the U.S. So let's take a look at a different type of example, a dirty bomb. So can a terrorist explode a tank of radioactive material in the middle of a city and make the city uninhabitable for the foreseeable future? Is that possible? So a device that releases large amounts of radioactivity is what we call a dirty bomb or a radiological weapon. And this scenario has received some attention in the news. It's certainly seen some attention in the movies, but it's actually harder to pull off than what you might think. So um, let's say that this is a terrorist who wants to spread radioactivity over 1 square kilometer and make it so that everyone um, gets radiation illness after 1 hour. So we want to affect 1 square kilometer, and so that's the terrorist goal. So the bomb would have to be approximately 1 meter in size. They would have to concentrate the radioactive material by a factor of 1 million. And the reason for this is that all this material would have to be very, very, very compact. Um, it takes quite a lot of radioactive material to do this. Once you do this, however, um, the radiation from this would be so strong from this. If you were to take plutonium and make it about 1 meter in size and then concentrate it to the fact that it's a million times stronger than normal plutonium. A person 1 meter away would get a lethal dose. So, because of that, this material would need to be shielded. We would have to encase it in lead. So, um, what we would have to do is we would have to use at least, um, well, here's the problem. Even if you put 2 centimeters of lead around it, uh, so if we built this box to place this highly concentrated radioactive material in, and we made the walls on it 2 centimeters thick, and again, this is a 1 meter cube basically, it would weigh 1.6 tons. And even if you did this, you would still get um, a lethal dose at 10 feet in 3 seconds. So, if a terrorist wanted to build this bomb, there's honestly, if you think about it, there's no way they could do it. You would have to build something that had thicker than 2 centimeter thick walls. Um, so it's going to weigh a lot more than 1.6 tons. You'd have to put it on a great big truck. You'd have to get the material in the U.S., but something that radioactive is going to have a pretty big radioactive signatures. I just don't see this ever happening. It would cost too much money, and it wouldn't do what a terrorist wants it to do. So I think we're all safe for the time being, anyways, from dirty bombs. That concludes video